We're going to talk about the fundamental theorem of arithmetic now. This is a very, very important result. We're not going to prove this just in the interests of time, but I will say if you're very interested, you should look this up. It's not beyond the level that we've talked about in this class. It's a little bit longer and a little bit more in depth, but you do have all the machinery available, all of the ideas, to be able to understand why this result is true. But it's a very important result. And it says that take any number that you like. It has a unique prime factorization. In fact, maybe I should say, let's make it not 1 here. So n isn't 1. So 1 doesn't really have a prime factorization. And what is a prime factorization? Well, that just means I can write the number n as a product of some prime numbers. And so we have some notation here, and I just want to talk about the notation. So I'm telling you that we have n can be written as the product of a bunch of primes to various exponents. So here I'm saying n, whatever k is, n can be written as the product of k primes, each to some exponent k. So we're thinking of the p's here as all of the primes that make up n, and e's as the number of those primes that you need to multiply to get n. So let me show you an example why this is true and then how this notation works. So let's look at the number 120. So if we wanted to find the prime factorization of it, a good idea is to do a tree diagram. So, or a tree factorization. So what you can do, find two factors of 120. It doesn't matter what they are. I picked 12 and 10. And we ask, are these prime? And if the answer is no, then we factor some more. Since they're composite, we can factor again. 10 we can factor into 5 times 2. We ask, are these prime? They are. So I give them a circle just to indicate that they are prime, and we can stop going down this branch. 12 isn't prime, it's composite. I could write it as, say, 4 times 3. 3 is prime, so I circle it. 4 is not, so I can factor it into 2 and 2. Both of these are prime. So the prime factorization of 120 is 2 times 2 times 2 times 3 times 5. So 2 times 2 times 2 is 2 cubed times 3 times 5. So in this notation, our k is 3 because we have 3 different prime factors. And the exponents, well, let's just write it down here. So P1 is 2, P2 is 3, and P3 is 5. So there are the 3 primes that make up 120. And I should say here, k is 3 because there are 3 primes. 2, 3, and 5. So we're going from P1, P2, P3. And the exponents for each of these, well, the first exponent, it's 2 times 2 times 2. So there are 3 copies of 2 multiplied together. There is only 1 copy of 3 and 1 copy of 5. So this is P1 to the power of E1, 2 to the power of 3, P2 to the power of E2, 3 to the power of 1. Remember, if there's no exponent, it's assumed to have an exponent of 1. And P3 to the power E3 is 5 to the power 1. And again, to show this is unique, or just to give an example, well, let's do a different factorization. Rather than 12 times 10, 120 is also 8 times 15. And we play the same game. 8 we can write as 2 times 4. We circle 2 since it's prime. 4 is 2 times 2. We circle both of these. 15 is 3 times 5. We circle both of those. And hey, look, we gather them all together. 2 times 2 times 2 times 3 times 5. Same factorization. In fact, no matter how you factor, you'll always end up with the same prime factorization. Which leads you to conclude that, hey, we can think of prime numbers as being the building blocks of composite numbers. We can always factor a composite number completely into a product of prime numbers. And we can do that in one way exactly. It's unique. So 120, its building blocks are 3 2s, 1 3, and 1 5.